Hi, welcome to the Signal Pad. I come across a lot of little interesting things here and there in the lab, which on their own may not be substantial enough to produce a full-length video, but nonetheless they are interesting and I want to show them to you and discuss them. So I thought maybe I put together a bunch of these every once in a while when I have enough of them and make a video about a collection of things that are not really related but on their own are quite interesting and we can discuss them. So for the first time ever, let's give it a try, an experimental video, and see how it goes. Here are 5 interesting things. Well, here's our first interesting thing. Now, this was sent to me by one of the viewers, and I'm quite grateful for that because now we get to learn about it and figure out how it works. And now, first of all, what is it? Well, it's an attenuator, and it's an attenuator 20 dB, and it has a frequency range of 12.4 to 18 gigahertz. Now, what makes this unique and special is that this attenuator has a continuous range, meaning that it doesn't have discrete steps. It may not be linear in dB as a function of the rotation of this knob, but it is continuously changing, and therefore you can accomplish essentially any value between roughly about 0 to 20 dB. So making continuous variable attenuators in microwave circuits is quite difficult. So how do they do this? How do they build this? Well, we have to cover a few different things before we can figure it out, and we're going to use all the clues from the different specification of this to see if we can figure it out before we take it apart. Well, first clue is that it has a limited frequency range, so that already tells us something. The second is that, well, the attenuation is, 20 to 20 dB. It's not that unusual, doesn't really help us that much. Now over here we can see 2 ports, port 1 and port 2. It's fully bidirectional, so it doesn't matter which way you insert the signal, it's going to do the attenuation in either direction. That's another clue. Uses SMA connectors, which is to be expected. Up to 18 gigahertz, it shouldn't be an issue. So how does it work? Well, I have shown a couple of different attenuators here on the channel. I've taken them apart. We've analyzed them in the past, so we can see that if there are any similarities between this and some of the other attenuators we have. So here's an example of one that we've seen on the channel. This is a discrete attenuator. This is a Hewlett-Packard one. This one works from DC to 18 gigahertz. So that's another clue. It means that this is ultra broadband. As soon as we know this starts from DC, we pretty much have guaranteed that this instrument, this device, is going to be a resistive divider, because if it was based on L's and C's, you would never be able to get such a broadband response that the impedance wouldn't be so broadband. So it's a resistive, not a reactive power splitter. Now this one is discrete. It goes up to 70 dB. You can turn this knob and it goes all the way down to 0, and it has 8 different positions, and therefore this will have 8 different ceramic hybrid circuits in here with different resistor ratios in order to give us a different attenuation. Now for a microwave resistive divider, it's not like a regular resistive divider, because you have to maintain a 50 ohm characteristic impedance, which means that you're not just changing one resistor, you have to change multiple resistors at the same time. So the ratio of those resistors will give you not just the attenuation, but it will also give you the 50 ohm impedance that you're looking for. So it's definitely not built like this. First of all, this is not continuous. If you want to make a continuous resistive microwave splitter, it'd be quite tough. You have to change the resistors at the same time with a single knob. It'll just be a mess. You would never be able to get the kind of result that you want. The characteristic impedance would change. It'll just be bad. So typically they're not built this way. And if they do, it would be highly specialized and very expensive. And I've shown mechanical versions of this, but I've taken them apart, where instead of this knob over here, you have a series of solenoids pushing pistons, which then touch different one of those ceramic hybrids, and therefore you get the attenuation that you're looking for by routing the signal through the ceramic hybrid that you want. So it's not like this one. Well, you can also do resistive splitters like this. Just another example. You can see in this one, they even tell you what the resistor values are. This is a 16.7. This is a 3-way, 2-way splitter, 3-port, very, very common. 50 ohms, ultra broadband. This is a 26.5 gigahertz one, DC to 26.5 gigahertz. And the reason it says 0.5 watt maximum on it is because, well, the resistive attenuators dissipate half the power in themselves, and therefore you lose 3 dB in the device, and you get therefore a 3 dB insertion loss. But this would be, you could use this as a 6 dB attenuator if you really wanted to, although nobody would. That would be quite a waste. This is used for power splitting. So it's not resistive. We can put that aside. We can do LC. Here's an LC version. This is a power splitter again, so you could use it as a attenuator. This one is a 180-degree hybrid, so the signal is split into 0 and 180 degrees. And as you can see, it's reactive. It's made of L's and C's. Now, if you wanted to build an attenuator with this, you could also do that. By the way, this resistor over here is probably to broaden the band between the ports or something. You have to look exactly to see how it is built. But nonetheless, it's definitely not built this way neither, because if you were to change, for example, let's say you were changing the dielectric constant of a capacitor, you would have to change the inductance at the same time to get the characteristic impedance to stay the same. Once again, it becomes a very mechanically different problem and quite difficult to solve, even though these are also can be fairly broadband, but they never go down to DC. So these will have a narrow frequency range of operation with respect to compared to the resistive one. The advantage is that they don't have nearly as much insertion loss. So that's the compromise made between the resistive and the non-resistive reactive power splitters. So it's probably not done this way neither. So then how the heck does this thing actually work? It's now becoming more of a challenge. So now you have to think about what are some of the ways to actually attenuate the signal. What happens to a microwave trace, and what are the mechanisms for power loss? Well, power can be lost because the wire in which you send the signal through is lossy and it will dissipate in the wire. But then how would I control that with the knob? I mean, I could increase the length of it, but then increasing the length of it will shift the phase and perhaps would also disturb the characteristic impedance if it's going to have a lot of losses in the wire itself. And if you make the wire losses very large, then the total resistance of the wire changes and no longer is a 50 ohm system. So it's probably not done that way. You could do it by radiating it off, by building a coupler, for instance, in which you change the distance so that the coupling changes. But that also changes the impedance again quite a bit. And that will be quite difficult to do as well. So it doesn't work like that neither. Well, here's a puzzle to you. Think about it a little bit. I'm going to take it apart and show you what's inside. All right, well, are you ready? Let's take a look at this. So I've taken the screws off and let's take this cap off. So right now it's set to its minimum attenuation. And check it out. Look at how simple it is. I mean, it should be obvious by now how it works. So let's examine it at its minimum attenuation. Here's the input and here's the output, or vice versa. And here's a strip of metal which is hanging in the air between the ground, which is at the bottom, and the ground, which would be at the top. When the cap is in place, you can see the cap has an indent there which then adjusts the ground distance, which means that this is working like a strip line. Now the dielectric of this strip line is air in this position, because you have air at the top and then you have the ground at the top and air at the bottom and then the ground at the bottom. And when I turn this, look at what happens. It's going to move this piece, and this piece is going to hug that line like that. So it goes both above and below it. So if I go to the maximum attenuation, which is here, it completely covers the strip line, meaning that this material is now sitting above, in between the ground and the microstrip, and at the bottom between the ground and the microstrip. And then that's it. That's the magic. This material has a very high dielectric loss tangent. So when you insert it in between the ground, you're replacing the air with this material. So the dielectric now becomes whatever this lossy material is, some kind of an RF absorber perhaps. And because it has a high dielectric loss tangent, the electric field between the strip line, which normally extends through the air and comes across and touches the ground planes, and that's how you get your characteristic impedance of 50 ohms, now has to go through this lossy material with a high dielectric loss tangent, and then you dissipate some of the energy, some of the power that's going because of the electric field in the dielectric itself. So that's one of the mechanisms of signal loss in microwave circuits. It's dielectric loss, and that's why making transmission lines, for example, in integrated circuits can be sometimes difficult if you don't have a proper ground plane and so on. Your components will dissipate energy directly into the substrate material. So here, by shifting this material in and out of the dielectric between air, you can change the attenuation. So when I'm somewhere around here, I'm kind of halfway, some of the electric field is going to go through the air, some of the electric field is going to interact with this material, and it's going to become lossy, so you get an attenuation between 0 to 20 dB. The closer I bring this, the more electric field that wraps around here is going to interact with this material, and it's going to increase the attenuation. So it'd be interesting to measure this and find out exactly what the curve at the attenuation is as a function of this. Maybe we can do this some other time. But you can clearly see now that the trick they use is by changing the dielectric constant of the material sitting between the, I should say, the dielectric loss tangent as well as the dielectric constant sitting between these two plates. Now, this obviously is going to change the characteristic impedance to some extent, but it's fairly reasonable. It stays reasonably good I think it's better than 10 dB return loss, so it's okay. And the length of this is not very long. And the length, of course, here also tells you that it has a limited frequency range of operation. So they've calculated and designed this based on the length and the distances and tuned it perfectly in that narrow frequency range. It's probably likely that outside of that frequency range, you don't get a lot of attenuation anymore because the length is too short, as well as the characteristic impedance perhaps changes a little bit too much. But nonetheless, that's pretty amazing, isn't it? So if I give you a little quick view on the side here, you can see what happens. There you go. If I move this in, it will hug this, and you can even see there's a little gap in the middle, which I bet they had to simulate and figure out exactly how to cut it to get the best response in the frequency range they want. Really quite nice, huh? I think these things are about maybe $800 or so when they were new. I don't think they sell them anymore. But that's it. One nice, really simple way of accomplishing variable attenuation at these high frequencies. That's pretty cool. All right, let's go to the next thing. Well, I'm actually a really big fan of chemistry, and I used to do a lot of chemical experiments when I was younger, and I have a lot of these different kinds of glass. So this is a distillation column, and I'm showing this to you as a reference, and a lot of distillation columns are essentially the same. So if you look at it, the idea is that you want to have a lot of surface area, so that if you have a vapor of some kind, you can pass the vapor, for example, in this instance, you would push the vapor through here, it would go through this column of glass, and it would come all the way to the top. You can see it circles back down, and it would come at the bottom. And then you would put a cold liquid into the outer layer of this, and that would be in touch with this spiral of glass, and it will condense, and then the liquid will come at the bottom. So you can imagine the efficiency of something like this is going to depend on how much surface area you have between the column of water that's filling all around this spiral shape there, and of course how much heat exchange you can get from it. So this is a fairly good one, actually. This is a fairly efficient one, but this is nothing compared to something else that I've recently scored from eBay. These things are normally really expensive when you buy them, and this is now a real distillation column. So if you look at this, at first it looks kind of like the other one, but instead of having double, this is a triple layer distillation column. So you have to look very carefully to see it. So let me focus over here a little bit so you can see how it actually has 4 distinct layers. So here's the layer at the very top, then there is another one just underneath it, and then the spiral will begin, and then there's the core of the spiral when the fluid returns. Meaning that if you want to do any kind of distillation with this, you get multiple chances where the vapor will be in touch with the cold liquid. So for example, in this case, let's say that you would use this port here and the port all the way at the end here to put the cold liquid in. Now the cold liquid will then fill the outer layer. It will go also through the spring glass and the center of the spring glass before it comes out of the other end. So the spiral, the core of the spiral, and the outer shell will be filled with, let's say, with cold water. And then if you put your vapor through here, it will have a chance of touching the cold water from the outside of the column and from the inside of the column twice. And that would give you a huge amount of heat exchange between the two columns. So I bought this for some experiments that I want to do. And I've always wondered if doing some chemistry kind of experiments here on the channel would be something that the viewers would be interested in, because it's something that I've always really enjoyed to do. Now these are extremely fragile, and one of the ways they ship this is that they fill it with salt. So they fill the whole thing with salt so that when there's vibration, salt, a particle would not allow this glass to rattle and hit each other, and afterwards you just wash it and the salt comes out without any problems. So that's how these things are shipped. Unfortunately, I actually bought one, and when it arrived it was already broken, and I had to get another one. And these things can be thousands of dollars when new. I got a reasonably good deal from this, and you can do some ultra high efficiency distillation with a triple column like this, and it's just awesome. It looks really, really cool. Let me give you a quick look across it. You can see it's just, I can't even quite understand how they built this because I don't see where the joints or the seams are. This is just an absolute nightmare for glass blowing. And it turns out that there's some fog in here, by the way. Some water has been evaporating in it. But this is done in New Jersey. This is from Ace Glass, and a lot of really high-tech glass industry here is in here in New Jersey. A couple of different companies make these things. So I thought you'd like to see it, and also give me some feedback on if you like chemistry experiments. Some really cool things can be done with instruments like this. So now let's switch gear to optics. And this is a WDM wavelength splitter. Now WDM is wavelength division multiplexing, is a technique of putting multiple wavelengths into the same fiber. Each wavelength then carries information from an optical link and they don't interfere with each other. And this is because fiber optics are broadband and it can have a really wide range of wavelengths that travel through them. Now I've done a video on WDM and I've done some experiments showing you the concepts of WDM and how dual polarization WDM systems actually work in order to increase the capacity of fiber optic networks. You have to go and find that video so you can see it, but I've never taken apart a WDM AWG before. So now this is an AWG system. AWG is arrayed waveguide grading, meaning that there is an array of waveguides, which is our optical waveguides, which allow you to separate the wavelengths together. So let's look at this device and see how it works. By the way, this is a really old device. This is from 2001, July of 2001. So that's really, I know, about 17 years ago. That's quite amazing. So let's look over here. So there's a single fiber coming in. That's just one fiber going into this device. An array of fibers comes out of this device, which then you can see goes around and around and splits into all these colored waveguide, colored fiber optics. Now these colors obviously don't mean anything. That's just a color paint on the outside of these fiber optics, and they've changed the color so you don't lose track of which one is which. All of these wavelengths are in the infrared. They're invisible anyway. The notion of color to our eyes doesn't really mean anything. But indeed, they are being separated by wavelength. So in a way, they're being separated by color. So the single wavelength coming in and going out. So how does this actually do that? Well, let's take it apart, take a look at it. I've already taken the cover off, and there it is. And at first, it doesn't really look like much. But this is a PLC. PLC is a planar light wave component or a circuit, planar light wave circuit. It means that the optical processing is done on a plane, and it's a planar device. It's not a 3D device. And this is fabricated using photolithography techniques. And that's very important because you're dealing with things that are wavelengths apart in the nanometer range, and therefore you need sub-nanometer precision to build these devices so that you can actually be able to do grading at the optical level. And that's why this is difficult to make. So you can see over here the fiber comes in here and it couples into this PLC device, and then out of this PLC device comes out a fiber. So what's actually inside this PLC device anyway? Well, let me first show you the principle before I focus in onto it. I'm not really supposed to be putting this on top of it, but this is a dead device anyway. So here it is. So the single fiber comes in. There's a slab which spreads the light, and these lights hit all of these waveguides. And these waveguides, that's where the name array waveguide comes from, because you have an array of these waveguides. So the light coming over here has multiple wavelengths already in it. And all these wavelengths enter at the same time into all of these fibers. So all these fibers carry the same information as the initial fiber does. But the length of the fibers are not the same. Therefore, there's going to be a phase shift introduced, delay introduced, at the end of this fiber where they join back together into this slab. Now, that means that different wavelengths are going to be at a different phase when they enter the slab, because their wavelengths are different, the length is different, delay is different, so therefore the phase will be different. So depending on the wavelength, you're going to have a different incident phase. Now, all those lights entered into this slab at the same time again, and because their phases are different, and because these dimensions are controlled very carefully, they're going to constructively and destructively interfere with each other and focus at a different point on the other side of the slab, depending on the wavelength. That's the key here. The key is that because the delay is different through the different array waveguides, when they mix back together, they're going to focus at a different point on the other side of the slab. And then you align the different fibers on the other side very carefully to line up where you would know the different wavelengths are going to focus. So this constructive destructive interference allows you to actually separate the wavelengths. It's brilliant, right? It's so simple, and it makes perfect sense that light would do this. I mean, actually, it's not just about light. Any electromagnetic wave would do this. And this kind of destructive interference is often used in optical PLC devices like this one. So therefore, you can build a wavelength separator. Now, this is a really simplified model of this. Sometimes they build two AWGs with different lengths and they combine them. There are a lot of tricks to be played. The design of these slabs are quite interesting. These are essentially light is trapped in these waveguide pieces because of the changes in the dielectric constant between the material. And there are tons of challenges in building these things. I won't go into the details of that, but I am going to see if I can rearrange the camera and if there's a way to get a closer look at this and we can see some of the features of the surface or not. So let me see if I can get this, and if you look very carefully, you might be able to see the waveguides. There you go, you can see them at the top. And they of course reflect the light. There you go, you can see them much better now. They reflect the light differently because of the fact that the distances between the waveguides themselves are comparable to visible light. So you get this rainbow effect as well, which is a grading mirror effect. I've talked about grading mirrors and grading lenses a lot in some of my other videos too. So there's a whole bunch of information about that as well that you can see. So the light coming in, if I find my pointer here, the light coming over here, the slab is right around this area. Here's all the AWG all the way up here, and there's actually one at the bottom. There's two of them in this case, and then the light that comes in there goes down and up and back into that one. So really neat, isn't it? Now this is not the only thing that is at play here. Unfortunately, things are quite a bit more complicated, and one of the complications comes from the fact that thermally the phase will be different, and therefore if you don't keep this at a precise temperature, you will get nothing out of the WDM splitter. Basically, it wouldn't line up, the delays wouldn't line up, and therefore where you would expect the constructive interference to happen to separate the wavelengths actually wouldn't happen there. So this is sitting on top of a Peltier device. So there's a TIC, thermoelectric, the TEC, thermoelectric cooler at the bottom of this with a feedback controller. You can see the pins are controlled at the bottom over here. So there's temperature monitor devices there. There is Peltier coolers. There's heat sink material distributing, keeping the temperature quite constant. You can see they're cooling the bottom of this very carefully, and they put this in a loop and they control the temperature precisely to where it's supposed to operate. I believe this device is at 76 degrees Celsius, and that's the only way it would work. If you don't do this, then you're going to get nothing out of it. So thermally closing these loop of these devices is itself very tough. And of course, they run it at fairly high temperatures because these things are sitting in hot places. You want to be able to, you want to make sure that you're able to get it to the temperature you want. So yeah, this is pretty amazing stuff. And even though it's 17 years old, it doesn't matter. The principle of operation of the AWG PLC hasn't changed. It's going to be the same. Now, there's a lot of other fancy things that have been introduced since then. But I also happen to have the wavelength response of this too. And here is the measured result of this. I'm not going to be able to measure. This is difficult to measure. You have to have a tunable laser. It's a tough measurement to do. So here's the loss and here's the wavelength. Now these are 50 gigahertz spaced. So you can see there is 8 channels. This is an 8-channel WDM splitter. And you can see that at 50 gigahertz spacing, which will correspond to a certain wavelength splitting, you have very little loss coming out of each of those cables. So if I look at only one of the outputs, I will only see one of these, and then it will not pass any of the other wavelengths. That's how the wavelengths are split into the 8 channels, which is quite amazing, isn't it? So that way you can put, by the way, 50 gigahertz is a ton of bandwidth when you think about how much data you can put into 50 gigahertz of bandwidth. I mean, you can put hundreds of gigabits per second if you wanted to at multi-level signaling, but at the very least, you can easily put a 100G link through it. So you would have a 100G link through going through all of these things using PAM4 or something like that. But we may be pushing it a little bit, but it is possible. And here you can see the spacing in 50 gigahertz, and there's a gap in the middle, and then the other 4 channels. So that we have even a full characterization of this. And the attenuation is going to be enormous. So if you're 50 gigahertz apart, at 50 gigahertz in the next channel, you're going to have 40 dB of optical attenuation between the 2 channels, which is quite significant. The crossover point is at about 20 dB loss there. So yeah, there is some insertion loss associated with this, which is bad. Of course, you don't want to lose optical power. It looks like it's about 3 dB, which is significant. So yeah, this is an old device, so this would be expected not to be the best thing ever made. But there it is. It's quite an amazing little thing, and hope you like seeing inside of a WDM AWG PLC unit, which is exactly what this is. Hopefully we can test it one day in the lab, but it's cool to see inside one. So here's something unusual. While I was at the IMS conference, one of the viewers who's watching my videos came up to me, and he was talking to me about the different videos I'm making, and he had a presentation at the IMS conference, and he gave me a prototype of the device he was presenting. He's a very nice guy. I'm going to link to his presentation and to his paper if he agrees to it. So this is a waveguide. It's a fairly unusual waveguide. It's a PCB based one. It's a really thin strip, and if you look, it has an antenna embedded on it. This is a Vivaldi type antenna. You can tell by the shape. I'll talk about it in just a second. And there's one on the other side, and essentially you're launching a wave into this structure. This is a PCB waveguide style, and it supports multiple modes, and they're interested particularly in the mode E11 in the X direction. So that will allow the wave to propagate through. Now this is kind of like a regular waveguide in terms of its dimension relationships to the wavelengths it supports. Not quite one-to-one, but it's kind of getting close. So a regular waveguide that supports the same frequency band would be fairly smaller. Now this supports the D band. D band is from 110 to 170 gigahertz, used for communication, imaging, and so on. And these Vivaldi launches are optimized for essentially launching into the desired field in the E11 direction and getting that all the way through. On the other side, you have nothing. So this is very similar to a PCB, to a plastic waveguide, which people have explored even at higher frequencies. Now the wave is obviously not contained within the structure. It's wrapped around it in a way. So it sticks outside of this, but it gets confined by the material, its dimensions, the electric constant, and so on, so that it stays within the structure of this. Now this looks deceptively simple. It's actually quite a bit more complicated than it looks, and it's, by the way, it's quite small, as to be expected, because we're dealing with D band. And the Vivaldi launches at the end are similar to, here's a Vivaldi antenna. Look at the size of this one, so you can see the same structure here. This is a Vivaldi horn antenna, 2 to 18 gigahertz, and this Vivaldi over here is 110 to 170 gigahertz. Vivaldi is really broadband. That's why this one works from 2 to 18 gigahertz. It's quite a broadband structure. So this Vivaldi design here has been highly optimized. This is a coplanar waveguide launch that goes into the Vivaldi, which then launches into the PCB material here, and then gets confined within the in the E11 field, and then travels to the other side. This thing I think has about maybe 5 or 6 dB loss, or 3 dB loss. I can't quite remember, but you know, for sending a D band around, it's not too bad, and it's inexpensive. You can really etch this very easily. And the Vivaldi itself has a fairly complex structure, even though you can't see it. So here's the Vivaldi, here's half of it. So it's got this different tapering, and it's got these notches in there, and these notches help with frequency matching, everything required to get the response that they want. So you can see the effort that they go through to create this. And the purpose of creating a waveguide like this is to be able to send D-band around without using a rigid metallic waveguide. You can imagine this is a fraction of a cost of an actual D-band waveguide, and coax wouldn't work, of course. Coax would be significantly more lossy, and anyway, there's no real coax that would work at the D-band. Anyway, everything has to be in waveguide, essentially. So yeah, it's a cool technology, similar to plastic waveguides, flexible, can be wrapped around material. Now, when this is supporting a wave, when there is a wave going through it, if you hold it with your finger like this, you're going to completely destroy its loss. So it needs some clearance around it, as do plastic fibers, plastic waveguides, because the field is confined around it. But it's really interesting to see the 3D simulation showing how much the wave and the field goes beyond the structure is all in the paper. Really cool stuff, and just to see something like this inexpensive. He has a whole bunch of these. He gave me a whole bunch of them. Now I have no way of testing them in my lab, because first of all you need this coplanar transition here, so you either need to probe it or have a little device that they have designed to test it. So I don't have that, even if I did generating D-band here in my lab, maybe I can find some parts to do it, but it's quite difficult and expensive. So nonetheless, very cool thing to see, and I'll link to the paper, just one of the examples of the things you would find at IMS. And nice one, very nice guy also. So hopefully, if he agrees, then I can release his name as well, and you can see some of the other work he's done. So the last thing I want to show you is this bill. This is a Canadian $100 bill, and you can do this with any of the new Canadian money. So this particular money was created, I think, about a couple of years ago, and the Canadian money is now all plastic, which is quite amazing because it's so resilient. You can wash it and it's quite tear-proof. It's packed with security features. It's got transparent regions. It's got different holograms with the number of the actual value of the bill written all over it. You can see different buildings. Here, I believe this is a building in Ottawa. Here's the picture of the Prime Minister. You can see the hologram here. The Prime Minister was from 1911 to 1920. At the back, we have the celebration of insulin being shown here. There's a lot of scientific data often displayed on Canadian money, which I really, really like, better than anything else, really, in my opinion. So having said that, there is another cool security feature in the Canadian money worth noting. There's a little semi-transparent maple leaf here in the corner, and in the middle of it, there's a little circle. It turns out that this circle has grading on it. It's a grading lens type of surface that they have created. The lithography of a grading lens is difficult, because you need to interact with wavelengths of light. And I've talked about grading mirrors and grading lenses and films many times. And what these gratings do, because they're comparable to the wavelength of light, they allow for interaction of light with itself to create destructive and constructive interference. And you can actually create patterns if you cleverly grade this, which is exactly what they have done as another feature in the money. Which means if I pass coherent light through it, like laser through it, I would be able to get a very nice constructive destructive pattern and see what it says. Well, let's try it. I have a laser pointer here. So what I'm going to do is I'm going to shine the laser pointer directly through here, and we're going to display, or we're going to shine and see what comes to the other side on some flat surface from a little bit of a distance away. So let's go. I'm going to focus out here so we can see it. There it is. So I'm going to shine the laser, and let's see what happens. Here we go. And check it out. You can see it, I hope. It says 100. It says $100. So it actually displays the value of the money if you shine light through it. Isn't it just amazing they have gone through the effort of doing this? All the bills actually do this, not just a $100 bill. I believe at the beginning it was only supposed to be the $100 because it's an expensive thing to add to the money. But it's really quite amazing. Now, because these gratings are going to be, depending on the wavelength, you're going to get a different distance between the constructive and destructive interference, so that the size of that $100 mark that you saw will be different depending on the wavelength. So if you were to look at a light source that's broad spectrum, like a white LED, you will see a rainbow pattern as the light separates, but each of the wavelengths that comes from the LED will then say $100 bill, but they're all going to be superimposed. So it'll be really difficult to see what it says if you look through it with your eye. But by shining a laser, which is a monochromatic single wavelength, you can see the pattern emerge. Now it looks much nicer in person than it does on the camera, because here I have my exposure to auto and it's not doing a very good job in adjusting it. But it's really pretty amazing, isn't it? And this really goes to the heart of one of the things that I've always noticed, that science is everywhere, and all it takes is for you to look for it. And if you look for science, if I can get this to focus, you will be able to find it. And there is amazing, wonderful things all around us. And I think it's the inquisitive nature of human beings that ultimately is going to give us the ability to discover all these things. So if you look for amazing science, you'll find it, no matter where it is. All right, I hope you enjoyed that. And as you saw, a lot of these components have to do with, well, you guys have sent me these or wanted me to talk about them. So if you have stuff like this that you want me to take apart and discuss, let me know. I'll give you an address where you can send it, and then we can make more of these videos on their own. Or if you want to support the channel on Patreon, I can buy these little things here and there, take them apart and make this collection of videos, which I think are quite fun, and don't take too much effort to produce, because they're shorter, but I think they have a lot of information in them. So if you like it, let me know in the comment section and we'll do more.